A water molecule is bent, while carbon dioxide is linear. Why is that? Both consist of only 3 atoms. What's even more intriguing is this. If water molecules were linear, life on Earth might not exist as we know it. Today, we'll use a visual simulator to uncover the invisible force behind molecular shapes, known as VSEPR Theory. Its full name is the Valence shell electron pair repulsion theory. It may sound complicated, but its core idea is simple. Electron pairs carry negative charges and repel each other, so they try to stay as far apart as possible. Imagine several balloons with the same charge tied together. They automatically push apart to find the most comfortable positions. The electron pairs in a molecule behave similarly. This mutual repulsion ultimately determines how atoms arrange themselves in space, the molecular shape we observe. Let's start with the simplest example, the carbon dioxide molecule. A carbon atom is sitting in the center, bonded to 2 oxygen atoms on either side. The central carbon is surrounded by 2 sets of electron pairs, forming 2 carbon-oxygen double bonds. How can these 2 sets stay farthest apart? By forming a straight line, a bond angle of 180 degrees, perfectly symmetrical. This is a linear molecule. Next, consider the methane molecule, a central carbon atom bonded to 4 hydrogen atoms with 4 sets of electron pairs in total. How can these 4 sets arrange themselves to maximize distance? By extending toward the 4 corners of space, forming a regular tetrahedron. The bond angle is 109.5 degrees, the golden angle of a tetrahedron. All bond angles are equal, most symmetrical and stable. So far, the pattern seems simple. The number of electron pairs determines the molecular shape, striving for symmetry. But what if some of these electron pairs are not involved in bonding? Here's where the troublemaker comes in. Lone pairs of electrons. Bonding electron pairs are held firmly between 2 atomic nuclei, staying neatly in the middle. Lone pairs, however, belong solely to the central atom. With nothing pulling them back, their electron cloud is more spread out, taking up more space and exerting stronger repulsion. Keep this in mind, you'll see it repeatedly causing trouble. Look at the ammonia molecule, a nitrogen atom bonded to 3 hydrogen atoms. But nitrogen also has an invisible lone pair, making 4 sets of electron pairs in total. Shouldn't that be a tetrahedron? Here's the catch. That lone pair is so dominant that it strongly repels the 3 NH bonds, pushing them downward. As a result, while the electron geometry remains tetrahedral, including the lone pair position, the molecular shape, considering only the atoms, becomes a trigonal pyramid. The bond angle shrinks from 109.5 degrees to about 107 degrees. What happens with one more lone pair? That's the water molecule, an oxygen atom bonded to 2 hydrogen atoms, but oxygen carries 2 lone pairs. These 2 bully pairs work together to squeeze the only 2 OH bonds even closer. Thus, the electron geometry is still tetrahedral, but the molecular shape becomes a bent V shape. The bond angle is compressed to just about 104.5 degrees. The more lone pairs, the more severely the bond angles are compressed. This is why water is bent while carbon dioxide is linear. Lone pairs are making trouble. To predict molecular shapes using VSEPR theory, just follow 3 steps. 1. Count the electron pairs around the central atom, including both bonding pairs and lone pairs. 2. Determine the electron geometry based on the total number of electron pairs. 2 pairs, linear. 3 pairs, trigonal planar. 4 pairs, tetrahedral. 5 pairs, trigonal bipyramidal. 6 pairs, octahedral. And so on. 3. Identify the molecular shape by ignoring lone pairs and focusing only on the arrangement of atoms. From linear to tetrahedral, trigonal pyramidal to V-shaped, the diverse forms of molecules all arise from the microscopic tug-of-war of electron pair repulsion. Finally, a challenge for you. What is the molecular shape of hydrogen sulfide? Share your answer in the comments.